think it's time now. So, yeah.
Good morning. A very warm welcome to all. On behalf of Ministry of New and Renewable Energy, I welcome Mr. Tony Saba for a very special session titled Rethinking Energy 2020-2030. 100% solar, wind, and batteries is just the beginning at this third RE Global Invest 2020. Ladies and gentlemen, as you are all aware, Mr. Tony Saba is a world-renowned thought leader, author, speaker, educator, angel investor, and a Silicon Valley entrepreneur. He is the author of the Amazon best-selling book, Clean Disruption of Energy and Transportation, Solar Trillions and Winners Take All, and co-author of Rethinking Transportation 2020-2030, Rethinking Food and Agriculture 2020-2030, Rethinking Humanity, 5 Foundational Sector Disruptions, the Life Cycle on Civilizations, and the Coming Age of Freedom, and the list goes on. Mr. Saba is a recipient of many awards, including the Savvy Award 2019, Solar Future Today's Visionary Influence Award 2018, and Clean Energy Actions 2017 Sunshine Award. His work focuses on technology, disruption, the convergence of technologies, business model innovation, and product innovation that is leading to the disruption of the world's major industries. He has been a keynote speaker at various events, organizations including Google, European Commission, Davos COP21, CLSA, JP Morgan, and so on. He has taught thousands of entrepreneurs and corporate leaders at the Stanford Continuing Studies. Without taking much of his precious time, I now invite Mr. Tony Saba to address the gathering. The floor is yours, Mr. Tony. Thank you.
Thank you, Joint Secretary Dinesh Jaggale. Thank you so much for that kind introduction. Secretary Minister Indu Shekhar Chaturvedi, thank you so much for inviting me, and Joint Secretary Banu Pratap Yadav. Distinguished audience, we're on the cusp of the deepest, fastest transformation of civilization in history. In the 2020s, key technologies will converge to completely disrupt the 5 foundational sectors of the economy: information, energy, transportation, food, and material. Production costs will come down by about 10x across the board, and resource usage and waste will also come down by about 10x. This is not another industrial revolution. This is a fundamental disruption of the extraction system that we have used over the last 10,000 years. And we are going to create a fundamentally new system that we call creation, in which the building blocks are going to be photons and electrons and bits, not coal and oil and steel. And we will finally have an opportunity to solve the world's most intractable problems, such as poverty, environmental degradation, and inequality. And I base this on my recent book, Rethinking Humanity, where we looked at 10,000 years of disruptions at all levels: product, sector, and societal levels. So let me walk you through disruption first, what the patterns of change are. Then I'll walk you through 100% solar, wind, and batteries, and how this applies to India. So those of you who know my work, this is 1900 New York City. There is one car in this picture in a sea of horses, just one car. Just 13 years later, there is one horse in a sea of cars. Just that's all it took for the car to disrupt a 9,000-year-old industry, the horse transportation industry. Now, this is how technology disruption happens. We go through an equilibrium. In that, for instance, in energy, we have a grid, and we've known that for about 100 years. There is a convergence of technologies that open up a vast new possibility space. Now, not everybody sees that space, but entrepreneurs And pioneers and investors may see that space and they rush in to develop products and services. They enter the market, they keep pushing costs down and capabilities up until it ruptures the existing equilibrium. Soon after that, the new breaks through very quickly and the old collapses, and the new essentially becomes the new equilibrium. And that's how disruptions have happened for 10,000 years. Now, let me walk you through that car disruption. There was a convergence, tire, steel, combustion engine, they all improved over the previous few decades in cost and capabilities. For instance, when the car came out in 1896 or so, over the following 12 years, the cost per horsepower came down by about 50 times in just 12 years. And then it tipped. S-curve adoption, it always happens as S-curves. Now, in all of America, it took about 20 years for cars to go from almost nothing to 95% of the market, just 20 years. But more interestingly, the car market share went from about 11 to 81% in just 10 years. So essentially, the disruption happened over just one decade. Now, this is more than 100 years ago, right? And this happened while we built two new industries, auto and oil. We built a brand new road infrastructure. We fought a major war and a major pandemic, the one from 1918 to 19. And in between all that, the disruption happened in just 10 years. Another feature of disruption is that it is a phase change to a new system with new properties. What does that mean? It means that the new system is not a one-to-one substitution. So the mainstream analysts at the time would have said that cars were just faster horses, but they were not. The new car transportation system was dramatically larger, was 10 to 100 times larger than the horse transportation system. Different properties, different metrics, and behaviors. So it was not a one-to-one substitution. And there were cascading ripple effects across society. So the car, of course, affected the economy. It affected how we date, where we live, how we live, geopolitics. I mean, the geopolitics of the 20th century were about oil, which, of course, came from the car. So disruptions affect pretty much everything across society. And yet, despite all of this evidence, the mainstream analysts keep making mistakes. And it's not just the analysts. I mean, you know that GE almost went bankrupt 2 years ago. GE Power collapsed. It lost $200 billion in market valuation because it bet on thermal power. And as you know, that market has already collapsed. But the interesting thing is that this collapse caught GE entirely by surprise. So the question that I ask myself is this: why do smart people at smart organizations consistently fail to anticipate, let alone lead market disruptions? And a very simple answer is this: it's the linear mindset. Forecasts that they, make are just linear extrapolations of the past. What does that mean? Well, look at the projections from the IEA. This is for solar. Every year, they make a 30-40% mistake. Every year. Then they go back and adjust and draw another straight line up to the future. And then that's another 30% mistake. And then they go back. So if you see the green line, that is reality. And it's looking like an S-curve. That's the beginning, the exponential beginning of an S-curve. And yet, the IEA is still giving us linear projections of the future. And also, this works for, or doesn't work for coal. Coal has been collapsing for more than a decade. And you see how this is an inverted S-curve? That is the S-curve of collapse. And every year, the EIA desperately tries to save coal by doing linear projections, and every year, coal keeps collapsing. And the last one is that red line, which of course is insane because this is the reality. This is the reality of collapse in every single disruption. Now, let me talk about my latest report, Rethinking Energy. 100% solar is just the beginning. Solar, wind, and battery is just the beginning, which I wrote with my colleague Adam Dorr. The question that we asked ourselves was this: is 100% solar, wind, and batteries is an electric power system powered only by solar, wind, and batteries possible? And if so, is it possible by 2030? Now, let me get started. Solar, unsubsidized, is already the cheapest source of energy ever in history. Solar is. Even solar with 4 hours of battery, what's called nearly firm, is cheaper than any other conventional form of energy. Not only that, it's cheaper than the operating costs of everything else. So at this point, investments in conventional energy make exactly no sense. But wait, there's more, right? The cost curve says that the cheapest source of energy is getting even cheaper. So solar went down, solar PV, by about 82% over the last 10 years, and we expect it to go down by another 72%. Wind went down by 46%, and we expect another 43% drop over the next 10 years. Batteries went down by 87%, and we expect another 80% over the next 10 years. So the cheapest sources of energy will become 70% cheaper over the next decade. And that is the convergence. But that doesn't answer the question. Is 100% solar, wind, and batteries possible, right? So let's look at that. We looked at 3 markets in the United States: California, Texas, and New England. So we looked at hourly data over 4 years, over 2 years, both in generation and also in demand. So all the demand in those 3 regions over 2 years. And we made a simulation of whether it was possible for 100% SWB. So one of the key answers was this: there are thousands of possible systems with 100% SWB, thousands. How do we choose? This is another key finding. It's what we call the clean energy U-curve. And this is the finding. There is a non-linear trade-off between generation and storage. Non-linear. It's not a one-to-one substitution, meaning the more generation you have, the less batteries you need. And the more batteries you need, the less generation you need. So all of this U-curve is 100% SWB systems. So we need to make the decision as to what is the least cost SWB system. And the answer is this. In those 3 regions, you only need 35 to 90 hours of battery storage. That's it. Now, you will hear a lot of, you need weeks or even months of storage. Not true. The fact is, all we need is 35 to 90 hours in those markets, right? You will hear soon what you need for India. In order to have 35 to 90 hours, that's less than 4 days of storage. You need to generate 3 to 5 times solar and wind. So not only that, 100% SWB, if we start building it next year, 2021, and we complete it 2030, is the cheapest possible electric power system, period. In California, it would only cost about $150 $15 billion to build the system to meet every single hour of every single day of current demand generation. This, by the way, is cheaper than maintaining the existing conventional system. Cheaper. So not only is SWB possible, it's also the cheapest possible system that we can build over the next 10 years. All over the US, it would cost about $2 trillion, less than that, which over 10 years is less than 1% of GDP. 1% of GDP. Again, it's less than maintaining the existing system. Now, I said that new systems have new properties. And the new energy system is just like that. It's not a one-to-one substitution. So just like the car was not a faster horse, the SWB system is not just cleaner conventional energy. It has completely different properties. How so? This is one of the most amazing properties of a solar, wind, and battery system. We call it superpower. Super abundant, near zero marginal cost of energy. How is that going to happen? Let me show you. In these three regions, for instance, we get, once that SWB system covers existing demand, it generates at least 100% more energy on 93% of every day. That's free, superabundant energy in excess of what would cover existing demand. In Texas, 93% of days. In New England, 64% of days. That is superabundant, clean, free energy. Now, today, the utilities would say we have to stop that power. We have to curtail that power. Now, why would you want to curtail free, clean power? I mean, solar PV is going to generate it, right? Why do you throw it away? Now, that is a sign that the existing system doesn't work. SWB does work, but the existing system that we built starting 100 years ago cannot handle the superabundance of solar, wind, and batteries. And this is just like the landline telephony business, if you know what that is, could not handle the internet. And it could not handle the cell phone, and it could not handle the smartphone. Essentially, the idea that we cannot handle a lot more energy, like we could not handle information, is insane. Now, this is what is rational. Steel producers are already turning to solar power. Why? Because it's super abundant and very, very cheap energy. And we're starting to see that in the United States, in Colorado, in Texas, and so on. So according to LightSource, a solar developer, most of their purchasers used to be utilities. Now it's 50-50 corporate and utilities. What does that mean? It means that corporations are attracted to superabundant, very, very cheap energy. And they're locating next to solar power plants, which is what is rational. And that's what is rational for superpower, whether it's steel mills, aluminum smelters, data centers, diamond manufacturing. It makes sense that if they need a lot of power, they should be located near superabundant, almost free power. Another key finding of superpower is that there is a disproportionate return to incremental investments in superpower. What does that mean? Once we invest in 100% superpower, solar, wind, and battery, which, as I said, is the cheapest possible system, when you invest an extra 20%, it can give you anywhere from 100 to 300% more superpower. we have never seen these economics in energy ever. This is more like information economics. No conventional form of energy can compete with this, where you invest 20% more and you get 200% more. They could not possibly compete. Now, superpower means this. California, for instance, the basic SWB 100 would meet today's electric power demand. But the superpower could meet all of the energy needs in electric transportation. So assuming that we go, which we will, all electric by 2030 or so, that could mean that superpower could essentially generate enough power at almost zero marginal cost to power every single electric mile in America. And if you add 20% investment, it could also cover residential heat, commercial heat, and some industrial heat. So superpower can power not just what is covered by electricity now, but pretty much every aspect of the economy, almost every aspect of the economy. So like in the past, this is a phase change to a new system. It's far larger, cleaner, and cheaper than the existing one. It can generate anywhere from 100 to 300% more power for less money. So now the linear forecast will, basically tell you that we're going this way. We're not. This is superpower. Now, conclusion so far: 100% solar, wind, and batteries is the cheapest energy system over the next 10 years. Superpower is disruptive to all forms of energy, and essentially every conventional form of electric power generation is already obsolete. Now, how is this going to work in India? Will it work in India? So we did the numbers this week. This is preliminary, but it gives us an idea of how this could work in India. This is the executive summary. India would only need 21 hours of energy storage, less than a day of energy storage. So again, anyone who tells you you need a week or a month or 6 months or whatever is not looking at the real evidence. All you need is about a day's worth of storage. And for that, you generate about 4.8x of solar and wind. Another finding is that it's mostly solar. So we need both solar and wind, but in a place like India, with awesome sunshine, it's mostly solar. It's about 10x solar. And the other thing, if you didn't notice, if you use that superpower, it's 1 cent, 1 US cent per kilowatt hour, 1 US cent per unit of energy. No one can compete with that. Not now, not ever. Now, what is the clean energy trade-off in India? Like I said, 21 hours of storage. That's it. And 4.8x of generation of solar and wind. This system would cost about $365 billion US dollars over the next 10 years to essentially create superpower in India. And how would superpower work? As you see here, there would be many, many days, and 97% of days with superpower generation of up to 2x current demand. So from January to about June, it would be anywhere from 75 to 100% extra generation for free. That's superpower. And what are the disproportionate returns? If India invests another 20%, it would need 30% more generating capacity, and it would generate 120% more superpower, even more superpower. And what would that cost? A total of 440 billion US dollars. So an extra 20% investment would return 120% more superpower. So let me rethink the future of energy with you And the future of energy is one of infinite possibilities. Photons are infinite. Can we grab that possibility? We're on the cusp of the deepest, fastest, most consequential disruption of energy in 100 years, since essentially the existing grid was first built. We can solve with superpower, water, desalination and cleaning, electric transportation, heat, recycling, waste, industry, large industry. We can generate energy that is super abundant for nearly free for all of those. Everywhere you have cheap and abundant energy, prosperity follows. And India and the world could solve essentially all of these sustainable development goals at the same time over the next 10 years or 15 years and get money back. Okay? This is not going to cost more money. We're going to get money back. So here's the answer. Here's the question. Can India become an energy superpower? The answer is this. You have the technologies that you need to become an energy superpower. It's your choice. Thank you.
Thank you, Mr. Stoney, for a very fascinating and mesmerizing 27 minutes of really brainstorming session, which really has thrown up the ideas that would take us and all of us to really think on how to become a superpower, as you have mentioned. You have given us certain figures, which we all will be deliberating now on how to get there. There are a few questions which have been really coming, and we have some time, and with you being here, one of the questions that has been coming is, what are the key factors that you think are leading to this price reduction? One is price reduction when you mentioned about both batteries, solar and wind. And the second is, what are the trends that you see in terms of the efficiency improvement in solar compared to what we are as of today?
Yeah, so disruptions like this one happen because, as I showed, the dramatic improvement in cost and capabilities, in this case of solar PV, and batteries mostly, and also for wind. One of the interesting things about this study is that it does not include breakthroughs. It does not include things like thin film or perovskite, which will accelerate this. We will get those technologies, for instance, perovskite, which will, promise to add another 5, 10, even 20% efficiency to solar PV. Once we get that, essentially this will be accelerated. The same thing with batteries. This study does not include breakthroughs in batteries. So over the next 10 years, we'll certainly get massive improvements, breakthrough, for instance, solid state lithium-ion batteries. And once we get that, this will be dramatically accelerated. Essentially, I've shown what can happen given existing technology cost curves. But I think this will even accelerate going forward.
Thank you. The second question that is coming is basically on the Indian policies, since you are now really presented the Indian demand over the last 2 years and how the demand varies. And specifically this question is the monsoon period, which the Indian subtropical climate has, and the southwest monsoon which prevails, which really sees a drastic reduction in the sunlight that it sees. So your prediction also says that the 21-hour storage is what is required. Do you feel that this for 3 to 4 months of monsoon will also be covered in this particular aspect?
We used actual generation of solar, wind, and battery from India, right? This is not a simulation of the weather. We used actual generation of solar and wind and actual demand to do these numbers. So yeah, it should. I mean, I think that when you do this, again, this was a first pass. When you do this on a more regional basis, you may get variations. I would not expect, again, because India has such great sunshine and so on, I would not expect massive deviations over this, just like we didn't see massive deviations, for instance, in New England, which has the poorest sunshine and wind in the United States, and yet it was still the cheapest possible form of energy, and it only needed a few days of storage. So even in the monsoon, I would expect those regions to have 2-3 days at most of storage, but I would not expect a whole lot more than that. I would be surprised. We would have to do those simulations, but I would not expect a massive deviation.
Thank you. And I see the clock. It was really, really wonderful, Mr. Tony Saba. Thank you very much on behalf of the Government of India, Ministry of New and Renewable Energy, to accepting our request and coming and delivering this very, very knowledgeful session on rethinking energy. I, on behalf of the entire ministry, once again, say thank you to you and would like to really meet you and take more ideas about how we can now move towards a superpower. Thank you,
Awesome.
ladies and gentlemen. Thank you.
I'm looking forward to that. Thank you for having me. Thank you.
Thank you.
Cheers.
Thank you.
Yeah.
Bye-bye.